PDF switch. And so I'll just let the first speaker come.
Okay, thank you very much. So my name is Arshdeep Singh. I'm a research fellow in the University of Surrey. So this work today I'm going to present on low complexity CNNs for acoustic scene classification. It's done with Professor Mark D. Plumley. And this work is sponsored by EPSRC and is part of a for Sound project. So typically, convolution neural networks have been widely employed in various applications and have shown remarkable performance as well. However, we see CNNs, they consume more power and have high latency, which arises from their large size and heavy computations. So this makes CNNs as a resource hungry because they have high computations. And if we see the impact of CNNs on environments, because of high computation, they emit more CO2. So because of this, CNNs are not environment friendly, and this makes is a real bottleneck if we are looking to deploy CNNs on resource constrained devices. For example, the context-aware services on smartphones or smart headphones, which uses acoustic scene classification kind of applications. So this work looks to come up with efficient CNNs to utilize the underlying resources effectively. This work focuses on DCASE task 1, which has a limit on parameters in terms of number of parameters and max. So we start with a baseline framework and follow simple 4 steps. Starting with the baseline framework, first step, we empirically select different filter sizes across layers and come up with a network which performs better than the baseline framework at a reduced number of computations. Then we perform pruning and quantization, where in pruning we assume that they exist redundant filters which produces similar outputs, which means that we can remove one of the filters from these redundant filters. And then subsequently we perform quantization to reduce the network size. So we observe that we can recover the accuracy at a reduced number of parameters compared to the network obtained in step 1. Then we observe that the network that we obtain after pruning different convolution layers, and if we assemble them, aggregate the scores from different networks, we can improve the overall performance. This way, the underlying resources, the upper limit given in the DCASE challenge, we can utilize the resources effectively. Finally, we observe that in the ensemble framework, when we have different number of networks, we observe that they exist intramodel redundancy, which means that if we produce output from different networks in terms of the feature maps, so we observe that they exist feature maps across networks, which produces similar feature maps, and hence we can further remove the redundancy or complexity from the ensemble framework by ignoring the repeatedly produced feature maps. So here, as shown here, the similar feature maps one of the similar feature maps from the other network can be removed in the ensemble. So this work looks to come up with a source-effective solution by optimally selecting the filter size, then performing pruning and quantization, then ensemble to improve the performance, and in the end, we remove the redundancy of the intermodels in the ensemble framework. So if you have any suggestions, discussions, please visit poster 1. Thank you very much.